Well, thanks very much for coming along this evening. It's a great pleasure, as always, to lecture to you about things I feel passionately about. This one I feel pretty passionately about, I've got to say. The trouble about when you write a new lecture, it always ends up being too long. So this lecture is too long. I shall therefore I go fast, right? And if it gets too long, I'll just stop. Okay, but anyway, there's some wonderful things I've discovered over the last little while preparing this. So this is a sort of general broad outline of what I'm going to be going through. What was happening in astronomy in 1209, 800 years ago? Then we'll run through these things before the Galilean Revolution, then the things which led up to Newton, the Cambridge Observatories, John Michell, one of the great unsung heroes, stars and television in Cambridge, Hoyle, radio astronomy, and lots more. Right? It's all built into this story. So let's go. Well, what was astronomy like in 1209? Well, in a word, Ptolemy and Aristotle ruled. Right? That was it. That was the received science of the epoch. This Earth was at the centre of the universe, and you can see this picture from one of the old tomes showing the Earth at the centre, and then going out with the Sun in one of the orbits about the Earth. Now, the reason this is important was that the Ptolemaic system, devised by Ptolemy, again in the very first century BC, he had developed a system for predicting the positions of the planets. And you had to take in all the detailed accounts of their rather complex motions. The amount of geometry that went into this was absolutely magnificent. They were great geometers, but they had strict rules. Only circles and only straight lines were allowed. So, by 1277, one of the really significant epochs was that the Rabbi Isaac ben Cid of Toledo, under the patronage of Alfonso X of Castile, also known as Alfonso the Wise. What a name. Alfonso the Wise. He commissioned the tables to be prepared in order to predict exactly religious festivals, when did spring actually happen, when did the vernal equinox happen, and so forth. And these were the famous Alphonsine Tables, based upon the type of geometry that you see here. You were only allowed to use circles and straight lines, but from that you were then able to predict exactly what the orbits of the planets were going to be. Now, the first bit of Cambridge science comes from Nicholas of Lynn of 1386, who came from King's Lynn, right, which is why he's Lynn. He actually did this work in Oxford, well, too bad, but he then moved to Cambridge later in life. And what he did was to produce this calendarium designed for use in astrologically based science of the time. So the tables were better than the original Alphonsines, but they included rules for synchronizing medical treatments with astronomical cycles. So what's the best day to have your blood let? That was an astrological, they required the tables to do that. So as I say, that's one of the earliest things. Now, the next important thing was the Tabulae Cantabrigienses of 1430 by John Holbrook, who was the master of St. Peter's College, now Peterhouse. He was the best Cambridge mathematician of his day, and he created yet more improved tables of the positions of the planets and the moon using, again, the Ptolemaic system. And in the history books, it is said that this work of Holbrook, and here it is, the first advance in science made in Cambridge. Right. We weren't very good until that time. And indeed, you will see from the troubles I'm having finding anything that happened before Newton, that indeed science, as we know it, was a bit of a struggle. He also used this to produce a nativity horoscope for Henry VI in his Codex Holbrookiensis. Now, I'm going to move up to the time of Newton and then go back a little bit and start again. But before the time of Newton, Jeremiah Horrocks was the most distinguished astronomer. He was at Emmanuel from 1632 to 35. He died only a couple of years later. And what he did was to demonstrate that the moon indeed had an elliptical orbit, just as Kepler had previously shown that Mars had an elliptical orbit about the sun. And even more spectacularly, he used the existing Ptolemaic tables to be able to predict that there was going to be the transit of Venus across the disk of the sun. That is seriously clever stuff, because it was not clear whether or not Venus would actually do it, but his calculations got it exactly on, and he made the first observations of the transit of Venus. Now, that's very important from the point of view of measuring exactly the distance to the sun from the Earth and so on. This picture here shows the transit of Venus in 2004, and there have only been 4 of them since Horrocks' time, so it really was a singular event. Now, just before we get to Newton, John Flamsteed, undergraduate at Jesus from 1670 to 1674, the first astronomer royal, appointed in 1675. He is most famous for his extreme bust-up with Newton. When I say extreme bust-up, this is the understatement of the century, right? That what happened was that he wouldn't release his observations, so Newton went and pinched them, did the analysis of the orbits, published them without letting Flamsteed see it. Flamsteed then went and collected every copy he could and burned them publicly. So, I was saying, things don't change, do they? Anyway, but Flamsteed was very, very important because his positions were among the best that were certainly improvements even over what we're about to talk about now. Now, we've got to go back a little bit to Tycho Brahe, the great Danish astronomer. He's one of my great heroes. I used to, when I was in Edinburgh, I had a gigantic original portrait of Tycho Brahe on my wall. And I would just look at him and say, if I can do as well as you, I've done well. Right? So he built the 2 observatories on the island of Hven. Here's the picture of him surrounded by his instruments. And he made systematic observations of the planets from 1576 to 1597. We believe that the resource to do this was about 2% of the gross national product of Denmark for 20 years. Now, that is decent funding for astronomy. Compare the UK figure, which is 0.8% for all science of the gross national product. So you understand why I admire Tycho Brahe. He was great. Now, he did what all of us would like to do. He then hired Kepler as his research assistant the year before his death. By this time, Kepler was already the greatest mathematician in Europe. And like all supervisors, he wanted Kepler to work on his theory of the motion of the planets, but Kepler was far too strong a personality. The next year, Tycho died, and Kepler set about analysing the data sets. Now, very quickly, within the next 5 or 6 years, Kepler derived the first 2 laws of planetary motion. These are the laws which tell us that the orbits of the planets are ellipses with the sun sitting in one focus, in the upper picture on the left. And the second is that if you draw the radius vector from the sun to the planet, then it sweeps out equal areas in equal times. And these are brilliant pieces of research done first of all on the orbit of Mars. He was already a strong Copernican, but this made him even more Copernican than ever. Now, here's the words of Tycho Brahe. We don't write scientific papers like this nowadays, but this is what he says about Tycho's observation. Divine Providence has granted us such a diligent observer in Tycho Brahe that his observations convicted his Ptolemaic calculation of an error of 8 arc minutes. It is only right that we should accept God's gift with a grateful mind, because these 8 arc minutes could not be ignored. They alone have led to a total reformation of astronomy. And, well, what this really means is that what Kepler had done was to try to fit circular orbits to the best observations available to Tycho's observations, and he couldn't do it. The best he could do by fiddling everything was to get 8 arc minutes error, and he knew that the observations were good to 1 to 2 arc minutes. So that's why he had to go from circular orbits to the elliptical orbits. Well, he then in 1619 wrote his great Harmony of the World, and that was the grand unified theorem theory of its time. And you can see the title page there with everything that was in this theorem. Geometry, architecture, music, philosophy, everything, metaphysics, it's all there, all in the Harmony of the World. He got through to about 7/8 of the way through the writing of the book, when suddenly, out of nowhere, there appears his third law, the crucial third law. Here's a modern version of it. There's the distances of the planets from the Sun relative to the distance of Earth from the Sun, which is given as 1, and the speed of the planets about the Sun. If you plot that on a logarithmic graph, log speed against log distance, you see the planets all line up beautifully, and you get a straight line through like that. And that is telling you that the speed of the planet is proportional to 1 over the square root of the distance of the planet from the Sun. That's Kepler's crucial third law. Now, Isaac Newton, again, undergraduate at Trinity, 1665 to 66, he did the following, aged 22. He discovered the binomial theorem, the integral and differential calculus, the theory of colour in optics, and the unification of celestial mechanics and the theory of gravity. Not bad, absolutely unbelievable, totally unbelievable. Now, this is all done, he'd actually had to go back to Woolsthorpe because the plague had hit in 1665, and so the university was evacuated, and he went home and did most of this work there. But it's a quite astonishing achievement. Now, there was a copy of Kepler's Harmonia Mundi in the Trinity Library, and Isaac Barrow, the first Lucasian professor of mathematics, drew Newton's attention to it. And that was crucial for the discovery of the law of gravity, because Kepler's third law told us that the speed of the planet was proportional to 1 over the square root of its distance, and Newton was able to work out the required centripetal balance between the force that was holding the planet in its orbit and the fact it would be thrown away by centrifugal force. He knew that had to be v squared over r. So you put the v into the v squared over r, and you get that the force must go as r to the minus 2. That's Newton's law of gravity in its primitive form. That was what it involved. Now, what Newton's genius was to show that once you've got that law, then the same force that holds the planets in their orbit is the same force that caused apples to fall to the ground. Because if you work out what the acceleration is under this law, compare it with the acceleration of the planets in their orbits, you'll find you get exactly the same constant. Quite out of this world. It's the first grand unification that happened in physics between celestial mechanics and gravity on Earth. Now, that is the primitive form. There were a number of problems that had to be solved before Newton was absolutely convinced he had it right, the orbits being ellipticals and things like that. But these were solved by the early 1680s, and then in his great Principia Mathematica, he drew it all together. As you see in this frontispiece, it was published by Samuel Pepys, who was then president of the Royal Society in 1687. So, that is the story of one of the most fantastic contributions of Cambridge to astronomy and to science. Here are the 3 laws of motion, which are enunciated by Newton in the Principia, and the extraordinary thing is that the words are identical to the words that we use today when we're teaching Newton's laws to undergraduates. It's a tremendous achievement. Now, what people may not be so familiar with was that Newton was also a brilliant experimenter. He was not a pleasant person. I don't think anyone will disagree with this statement. He was horrific. He was a really terrible person. There's one of the quotes in one of the biographies of Rumford where it says that he was the most unpleasant person in the whole history of science except for Newton. Because Newton really worked entirely on his own and very, very much a loner. But in his work on optics, he did the famous experimentum crucis, which showed that if you split up white light into its various component colours, and then take one of these colours, it won't be split up anymore. That was a crucial experiment. But he also realised that they were being bent by different amounts. And so if you've got a refracting telescope, then the different colours get refracted by different amounts through the lens, and you get a blurred image. His solution was to invent the all-reflecting telescope, because the reflected light doesn't have the same dispersion. And here's a picture of his telescope that he built and demonstrated to the Royal Society. On the top left, you will see his magnified image of a crown compared with the smaller crown to the right of it. So this is a brilliant piece of optics. And again, many telescopes use the same principle nowadays. So again, that's another major contribution to astronomy. Now, there's one other beautiful story that comes out of this. And it's to do with gravitational collapse, which is one of the key elements of modern theory of cosmology, the formation of structure of the universe. Richard Bentley was going to give the first series of Boyle lectures in memory of Robert Boyle with the aim of combating atheism. It was quite... And so Newton and Bentley had a correspondence, only a exchange of 4 letters, about whether the universe was going to be stable under Newton's law of gravity. Now, you see, gravity is always positive, always attractive. And therefore, if you just have a bit of stuff, it's going to collapse under gravity. So they agreed, first of all, the universe had to be infinite, because you had to make sure that nothing would collapse upon itself. So there hadn't to be any boundary on it, or so that you could balance all the forces. But they also noted, but suppose you displace a bit of matter closer to another, well, gravity takes over again, and the stuff collapses. So that even if you've got an infinite universe, and you spread things out fairly uniform, it's still going to be unstable. And as Edward Harrison wrote, Newton agreed with Bentley that Providence had designed a universe of infinite extent in which uniformly distributed stars stand poised in unstable equilibrium like needles on their points. That's the only way you could explain the existence of a universe that was static and not collapsing in on itself. Now, that statement was only quantified in the 20th century through the work of Jeans, Lemaitre, Tolman, and Lifshitz, and the answer is absolutely correct. A static universe is unstable, and the stuff in it will collapse. The good news is we need the stuff to collapse to make you and me. The bad news, you can't have a static universe. But fortunately, the universe is expanding, so it's all right. Okay, that's a different lecture. Okay, so Newton became the Lucasian Professor of Mathematics. The post was founded in 1663 by Henry Lucas, who was Cambridge University's Member of Parliament from 1639 to 1640. And here's a list of the Lucasian professors, a very, very distinguished list. I've just highlighted in blue some of the names that you may recognise. Sir Isaac Newton, again, Isaac Barrow resigned his chair so that Isaac Newton could take it up. Wouldn't happen nowadays, but there we are. There it is. Right. And then you can see the list of the other people on the right-hand side. Charles Babbage, inventor of the measuring engine. Stokes, Larmor, Paul Dirac, James Lighthill, and Stephen Hawking now holds the chair. In 1704, the Reverend Thomas Plume, he left money in his will to found the Plumian Chair of Astronomy and Experimental Philosophy. I like the term experimental philosophy. That's very, very nice. But you can see, again, a very distinguished set of people. I'm going to talk a little bit about Arthur Eddington and Fred Hoyle in this story. I'm not going to be able to get through everything. There's just so much in this story. But again, it's a very, very distinguished chair indeed. Now, the Plumian professor had to have access to observatories, and there were 2 observatories that were available to him. One was built on the Gatehouse of Trinity, and that operated from 1739 to 1797. I apologise for not having an engraving of it. Wonderful. Think of the Great Gate of Trinity with a large dome on top of it, and you have got exactly what it looked like. The problem was that people preferred to fire fireworks from the top of Trinity Great Gate and have fun and celebrations, so it didn't last all that long. But St. John's also had an observatory right into the mid-19th century, and again the university professor, Ptolemy professor, had access to these facilities. But the Cambridge Observatory was then built on the present site in West Cambridge in 1823. And most of the money, as often happens in these occasions, was spent on building a splendid building and not on instruments. So you ended up with a wonderful observatory with no telescopes. I wish I could say this never happened after that time, but it is not true. So again, there it is. Just imagine that the observatories with no instruments, and you've got the picture. So eventually, they did get, thanks to the work of Airy, they did get telescopes, in particular the Northumberland telescope. It's called the Cambridge Observatories, and the reason for that is that the Solar Physics Observatory in South Kensington was moved in 1930 to Cambridge, and then in 1946 they combined the Solar Observatory and the Cambridge Observatory to become the University Observatories. Now, moving on, the next thing, of course, was to work out what's the magnitude of Newton's gravitational constant. And one of the next heroes is Neville Maskelyne, who came up to St. Catherine's in 1749, and he became the fifth astronomer royal after Flamsteed. And he made some of the first measurements of Newton's gravitational constant using the attraction of mountains. And he did this. He went up to Scotland, not far from my hometown of Dundee. He went to Perthshire to use Schiehallion in order to measure the attraction of Schiehallion relative to the attraction of the Earth. And you could then measure the deflection of plumb lines to see what had happened. Now, here's a picture of Schiehallion, and on the left you will see me with hair, black hair, and our son and daughter, Mark and Sarah. Sarah's aged 4, Mark is aged 6. We bring them up tough, right? This was their first Monroes, right? but although they were terribly tiny, they enjoyed it in the end, and we got up to the top. And then here's the plaque also at the bottom of the mountain, erected on the 250th anniversary of the first measurements of Maskelyne, showing the deflection of the plumb lines, so you could measure the attraction of the mountains relative to the attraction of the Earth. And that was the first measurement of the gravitational constant, thanks to Maskelyne. Now, the next great hero is John Michell, who's undoubtedly one of the great unsung heroes of world astronomy. He was a fellow of Queen's College and fellow of the Royal Society in the same year as Henry Cavendish. Then in 1762 he was appointed Woodwardian Professor of Geology in Cambridge, and then when he married he had of course to leave Cambridge and became the rector of Thornhill in West Yorkshire from 1767 onwards. But his achievement is absolutely immense. And here are just 4 of the things which he did. He made the first physical measurement of the distances of the stars by using Saturn as an intermediate distance calibrator. See, the big problem is it's very difficult to measure distances relative to the sun because the sun is so bright. So what he did was to see that one of the distant stars was almost as bright as Saturn, and if you assume that Saturn is reflecting all the light that's incident from it, you can work out then what the relative distance is to the star and to Saturn are. Extremely clever stuff, right? But assuming that the star and the sun have got the same brightness. He introduced statistical techniques into stellar astronomy. He built the Cavendish experiment that was subsequently used by Cavendish, and he made the first suggestion of the possible existence of black holes. That's not bad going, right? Let's just look at 1 or 2 of these. Herschel had made star counts in order to just determine the structure of the Milky Way, and to be able to make that into a map of distances, he assumed all the stars had the same brightnesses. They were all the same brightnesses. He also didn't know about interstellar extinction, but let's forget about that. Now, In 1767, what John Michell showed was that Herschel's assumption had to be wrong, because he looked at bright star clusters and showed statistically that these could not be random associations. They had to be genuine physical phenomena. And that's the first time that statistics was used to demonstrate the reality of star clusters. They are not just randomly placed stars which happen to lie there. They were actually a physical association. And you could see a whole range of brightnesses of the stars because they were all at the same distances. He pointed that out before Herschel created his map of the galaxy. And of course, as you might expect, Herschel ignored it. Well, went ahead and produced the map of the galaxy anyway. In 1802, Herschel measured the magnitudes of visual binary stars and discovered that they had lots of differences in brightnesses, and agreed then with Michell. Then, after he'd made his observations of the 40-foot telescope, he showed that the stellar system was unbound. Herschel lost all faith in his map of the galaxy at all, and just gave up on that bit of science. Here's the picture of the original Cavendish experiment, which was built by Michell, and this produced the first genuine, unambiguous value of the gravitational constant made by Henry Cavendish. Again, Michell had died by the time the experiment was carried out by Cavendish. And then finally, here's what Michell wrote in 1783. He was studying the attraction of light by the sun. So what he's saying is, hence, the semi-diameter of a sphere of the same density with the sun, were to exceed the sun in proportion 500 to 1. That means if you take the sun and keep it the same density, but make it 500 times bigger radius, then a body falling from infinite height towards it would have acquired at its surface a greater velocity than that of light. And consequently, supposing light to be attracted by the same force in proportion to its inertia with other bodies, all light emitted from such a body would be made to return towards it by its own proper gravity. 1783. Okay? Relativity doesn't appear till 1905. No. General relativity doesn't appear until 1915. This is clever. Okay? Now, of course, the physics isn't exactly right, because the way that black holes work is different from actually being escape velocity, because the whole of space-time has got tied up. And that's why it's a black hole. But again, you get the same value that Michell got for the radius at which this should happen. So Michell is a great guy. I believe someone is writing his biography, but he's one of these very obscure people about whom very little is known. Now, carrying on, John Herschel. He was the pioneer of double stars, the son of William Herschel. And he was a student in Cambridge from 1811 to 1816, and apparently St. John's regard him as part of theirs, right? And so he's regarded as part of the Cambridge establishment. He did most of his work in South Africa, but he was a very brilliant scientist. And one of the first things which he was really interested in was the development of photography. Now, one of the most moving pictures I've got is this picture. Now, remember that the announcement of the discovery of photography was only made in 1839 in Britain by Fox Talbot and by, I've forgotten his name just at the moment, in Paris. But 1839 was the date. And within a month of that announcement being made, he took this picture through his bedroom window of his father's 40-foot telescope at Slough. And this is the original picture made by John Herschel at that time. This is a very expensive picture to get. The Ruddy Science Museum charged me £250 for this picture. You are lucky, right? And it's in my book, The Rotters, right? It really is wicked, right? But anyway, that's just life. But it's a tremendous picture. This was again reconstructed from the negatives in the 1890s, but it's one of the very, very first pictures, and it just so happens to show the great 40-foot telescope. Now, moving on to the 20th century, the next bit of important Cambridge connection I'm going to mention is the work of Henry Norris Russell, who came as a graduate student to Cambridge in the 1900-1910 period. And what he did was to work at the observatories with the Northumberland Telescope and work out the techniques for measuring photographic parallaxes. Now, by photographic parallaxes, what that means is you take photographs of the stars at one time, and then 6 months later you take another, or 3 months later you take another photograph, and hope to observe the motion of the stars on the photographic plate relative to the distant background stars. But this was normally done laboriously by refracting telescopes. This was using now photographic parallaxic techniques. And they were then able to measure the distances of about 300 stars by that technique. He then went back to Harvard and got the spectral types, essentially the temperatures of the stars, from Pickering and his team, including Annie Cannon, and produced this famous, what we now call the Hertzsprung-Russell diagram, the diagram which shows the luminosity of the stars on the vertical axis against essentially their temperatures. And the important point is that the stars don't lie all over the place on this diagram. Shown by the lines to guide the eye is what is known as the main sequence, and then there are stars up to the right which are known as the giant stars. And you will notice one little fellow down to here, there's one down there, right? That's the first white dwarf ever discovered. It's a very compact star, but very, very hot. Now, here's the modern version of the same diagram. You can just compare them. There's them. Not bad. Jolly good. I always like showing this diagram because this was obtained by the Hipparchus satellite of the European Space Agency, and Michael Perryman, who was the great hero of that story, was one of my graduate students. So, excellent Cambridge connection. So that's a lovely story. But you can see it's got this same very tight relationship between temperature along the bottom axis and luminosity up the vertical axis. Now, the understanding of that diagram was then one of the great challenges of the early part of the century. And the great hero is undoubtedly Arthur Eddington. And as I write here, almost single-handedly, he developed the equations and the solutions of these equations to describe how the stars work, long before many of the key bits of physics were really properly understood. Now, he was, again, an absolutely brilliant mathematician. He'd done everything that Cambridge could offer, went to the Royal Greenwich Observatory, and then came back again as the director of the observatories in round about 1911. Now, this period then from 1915 to 1926, he basically solved the problem of how the stars worked. Now, I'm not going to describe how that worked, except to say it's a miraculous piece of theoretical physics applied to the Hertzsprung-Russell diagram, but it was not achieved without considerable controversy. And I'll just give you a little bit of example of the sorts of controversy that went on. You see, the physical data to construct good stellar models just weren't available. For example, you need to know the dependence of the energy generation upon density and temperature, and you need to know the opacity of the stellar material, and none of that was known. So you needed to make sweeping approximations to make progress. Now, fortunately, Eddington, I've written down here, he had the right qualities of fearless imagination and technical skill to make the problems tractable. But they were big approximations. So, for example, in his standard model, Eddington made what Leon Mestel refers to as the hair-raising approximation that the pressure of radiation is a constant fraction of the total pressure throughout the star. Now, if you think about it, my God, how can that possibly be true? Because, we know that they've got different dependencies upon density and temperature. And it's no surprise, therefore, that there's a lot of heated debate about his models of stellar structure. In fact, he was lucky, and I think he probably knew instinctively it was going to turn out all right, because the forms of the mass-luminosity relation for stars depend remarkably weakly upon what laws you assume about energy production and the opacity law. You will almost get the right answer whatever you put in. But what it did mean, the fact that he could get good models, meant you could apply the laws of laboratory physics to the insides of the stars. And that in itself is a tremendous advance. But it wasn't all smooth going. Here's what's published in the Observatory magazine. May I conclude by assuring Professor Eddington, this is from Jeans to Eddington, may I conclude by assuring Professor Eddington, it would give me a great pleasure if he could remove a long-standing source of friction between us by abstaining in future from making wild attacks on my work, which he cannot substantiate, and by making the usual acknowledgments whenever he finds that my previous work is of use to him. I attach all the more importance to the second part of this request because I find that some of the most fruitful ideas which I have introduced into astronomical physics, for example, the annihilation of matter as the source of stellar energy and highly dissociated atoms and free electrons as the substance, are now fairly generally attributed to Professor Eddington. This is one of the milder examples of the debate that went on. And again, that was going to later influence things. This mode of what I would call robust academic discourse was just part of the way that the science was conducted. And it had a terrible effect on people like Chandrasekhar when he came to Cambridge and found that the people were being extremely rude to each other, but it was just all part of a game, basically. Now, I'm going to leap to after the Second World War now, leaving out lots and lots of things just because there's not time to do everything. But the impact of the Second World War really had a gigantic effect upon the whole of science, and again, astronomy in particular, benefited enormously from the advances, particularly in radio techniques, and the fact that one could put rockets above the Earth's atmosphere for astronomical observation. So the key things that happened during the Second World War is that people became used to investment in pure science. Physics had won the war. People always say chemistry won the First World War, physics won the Second World War. And what it's saying is that the role of physics in again, enabling the war to be won was appreciated, and that then fed into the major investments in science after the Second World War. It was the very earliest parts of scientific computation, Bletchley Park and all of that. Astronomy then became part of big science, which needed larger resources to fund. And these things all contributed to many of the great and unexpected astronomical discoveries. Here's what Bernard Lovell wrote in 1987. The astronomers adopted an approach utterly different from that deriving from the pre-war environment. The involvement with massive operations had conditioned them to think and behave in ways which would have shocked the pre-war university administrators. In other words, they'd been spending vast sums of money in developing radar, in building battleships, and they got used to getting their own way because the nation needed it. And that philosophy they brought back to, and well, you can imagine the old schools not liking it when people said, well, anyway, you understand the problem. Now, in particular, I want to look at the origins of radio astronomy and then mix that up with the development of other things in Cambridge at the same time. So after the war, a number of the university groups began to investigate the cosmic radio noise, which had been discovered before the war by Jansky and Ryle. And the principal groups were in Cambridge, Manchester, and Sydney. But these people all came back from the war world experts in radio technology and radio techniques. And Martin Ryle, in particular in Cambridge, was the person who led the Cambridge effort. Well, here is one of the first radio telescopes built in Cambridge, at the rifle range, just behind where the University Rugby ground is now. It belongs to Jesus. And again, this is a radio telescope. There's Martin Ryle's house. He lived in Herschel Road there, and there it is, just there. Well, it was, these people just realized there was lots going on in the sky. The first Cambridge survey, here is Graham Smith and Martin Ryle building the 1C aerial, 1C standing for the first Cambridge aerial, and there it is there. That's, again, an array to observe the sky. By the early 1950s, largely thanks to the Australian radio astronomers, they knew that some of the discrete objects, the discrete radio emitters, were associated with strange, massive galaxies. And these are just a couple of the examples. And to make matters even worse, what Jennison and Dasgupta and Jodrell Banks showed was that the radio emission wasn't coming from the galaxies. They were coming from regions on either side of these rather massive galaxies. Now, this source was so far away that there were two immediate conclusions. One was they were so far away you could then use these objects for doing cosmology. And secondly, a whole new aspect of high-energy physics had to be invented to account for these sources, which are sources of radio emission of high-energy particles, magnetic fields, which was unlike anything in astrophysics before. So, the Cambridge astronomers, radio astronomers, started surveying the sky, and here's the 2C telescope, which was going to do a deep survey of the sky to find these very distant objects and do cosmology and to do this new radio astrophysics. And here's a wonderful picture of the radio group in the early 1950s. In the middle, here's Martin Ryle, here's Tony Hughes, here's Graham Smith, John Shakeshaft, John Baldwin, Peter Scheuer, lots of the key pioneers of Cambridge and elsewhere radio astronomy. Now, something different. Before I carry on that story, it was going to be used for cosmology. And in the meantime, in 1948, the steady-state cosmology had been invented by Fred Hoyle, Tommy Gold, and Herman Bondi. And here's a lovely note from Fred Hoyle's memoirs. In a sense, the steady-state theory may be said to have begun on the night when Bondi, Gold and I patronised one of the cinemas in Cambridge. The picture, if I remember rightly, was called The Dead of Night. It was a sequence of 4 ghost stories, seemingly disconnected as told by the several characters in the film, but with the interesting property that the end of the 4th story connected unexpectedly with the beginning of the 1st, thereby setting up the potential for a never-ending cycle. When the 3 of us returned that evening to Bondi's room in Trinity College, Gold suddenly said, "What if the universe is like that?" That's the origin of steady-state theory. And happened, again, in the cinema and in Bondi's rooms in Trinity. Now, you can formalize all of this, but what it ended up with a model for the universe, which was remarkably simple, in which the universe preserved the same appearance at all times, and the universe was expanding. We knew that by this time, but therefore matter had to continually replace the matter that was dispersing. Hoyle attributed that to the action of a creation field which he called C. Now, because of the unique nature of the model, it was extremely testable. And in particular, when you look far away, things should be the same as they are nearby. Now, in fact, it ends up that theory is not so different from the modern inflation theory, because it turns out the dynamics are rather simple. Let's skip that. Now, before we get back to the cosmology story, in the meantime, having got the idea of steady-state theory, Fred asked the question, where do all the elements come from? The prevailing thought was that they might have been cooked in the Big Bang, but Fred was trying to work out ways of making the elements with stars. Now, I think many of us consider this to be Fred Hoyle's greatest contribution to astrophysics and cosmology, that he predicted that you could make carbon by a very, very rare reaction in which 3 helium nuclei came together. Now, three body interactions like that are extremely rare. And so you had to do something to make them occur with a reasonable probability. Now, what he realized, that the cross-section for that occurring was extremely small, but he found that if there was a resonance which enabled the 2 alpha particles to increase their lifetime by a large factor, then you could wait for the 3rd one to come along, and then you would make carbon. And he worked out the mathematics of this and made the prediction of what the energy of that resonance should be in order for this to work. Now, when I talked with Willie Fowler about this, he said that when Fred was at Caltech at the time, when he mentioned this to the nuclear physicists, he said, look, forget it. The models of the atoms are lousy. The atoms of nuclear are terrible. We can't predict anything. But he was, Fred, predicting with absolute precision the number of MeV, the resonance energy, had to be if you were going to make carbon by bringing together 3 alpha particles. Ward-Whaling and his colleagues said, oh, well, we've got spare time on this, let's try it. And there was the resonance. It's one of the great predictions. This is pure genius. Now, Fred did a lot of other things, which have not been so successful, but this is astrophysics of the absolutely highest level. So that meant that you could then make all the elements in stars. So why did you need a Big Bang? Well, what happened next was the 2C survey was completed in Cambridge by 1955. Here is the picture of the radio sky. The open area is the southern hemisphere that we can see. And you could count the number of objects down to different limiting flux densities. And the key point here is that this is what you would expect in a uniform universe, and in what Martin and his colleagues observed was a huge excess at large distances. Now, in this Halley lecture of 1955, Martin and Ryle said this is a most remarkable and important result, but if we accept the conclusion that most of the radio stars are external to the galaxy, and this conclusion seems hard to avoid, there seems no way in which observations can be explained in terms of a steady-state theory. And this was the beginning of one hell of a battle between the proponents of steady-state theory and the evolutionary cosmologists. Now, that result came as a big surprise to the astronomical community, because the nature of these sources wasn't known. They were simply known as radio objects, and there was only 20 of them identified with nearby galaxies. How could you make these sweeping statements? And even worse was to come, because of the Australian astronomers, they made their surveys, and they discovered that the number counts, as we call them, were not as steep as the Cambridge counts. And in one of these sentences designed to make friends, we therefore conclude that discrepancies in the main reflect errors in the Cambridge catalogue, and accordingly deductions of cosmologic interest derived from its analysis are without foundation. This is great friends. So, my God, I actually joined the radio astronomy group just in the years after all this was happening. And if I use the word frosty relationships, that's being extremely polite. My God, it was quite something. Now, despite the ensuing controversy, it was already apparent that radio astronomy had the potential to do completely new types of astrophysical and cosmological studies. And so in 1956, the Radio Observatory moved to this used wartime in-ministry bomb site at Lord's Bridge. The Mullard company gave £100,000 in 1956 pounds to build the observatory, and that's why it's known as the Mullard Radio Astronomy Observatory. So here's the opening of the observatory with Martin Ryle on the left, Frisch, Appleton, the VC, Casimir, all very distinguished physicists. Here's Tony Hughes explaining how the 4C telescope works. People wore hats in those days. You see, it wouldn't look like this now, but this is the opening of the observatory, and this is how to celebrate. This is the celebration dinner in Keys, and if you look very closely there, you will find everyone in UK astronomy was there at the time. Lovell is there, the astronomer Ryle, Fred Hoyle was here. Everybody's here at the opening of the celebration dinner. And here's the 4C telescope, which is still standing, which was one of the first telescopes. Now, Martin's great genius was to develop the technique known as aperture synthesis, by which you can make big telescopes out of small telescopes. Provided you can preserve the phase information, you can reconstruct the maps of the sky by using lots of little telescopes than having to make a huge telescope that you couldn't build anyway. And this was demonstrated by a brilliant analysis that he and Neville did in 1962. And this is all done by little telescopes and then adding together the signals in the appropriate way. They used every receiver that they could get their hands on to be able to do this, and they used the EDSAC, first generation EDSAC computer, to actually do the computation. It couldn't have been done otherwise without the introduction of these computers. Soon after, one was able to make the source counts and show that indeed there was this evolutionary excess of sources. Just showing you again here, this is some of my own work. But when I joined Martin, he said, prove steady-state theory wrong. That was my PhD program. That was all. Now, between Martin Ryle and Fred Hoyle, you grew up very quickly, right, when you asked to do it. But anyway, the bottom line was all the standard models give the red line, and the observations were shown by these lines. And there was clearly a very strong discrepancy, which more or less tied up the whole story. So then Martin built the 1-mile telescope, which again produced some of the first maps of these radio sources. Again here, now the first aperture synthesis images showing this double structure of Cygnus A here, and here's an exploding star. Again, I was actually in the computer room when these first came off out of EDSAC. And oh my God, it works. This way of combining all the signals was a really fantastic achievement. And that same technique is now used in all the big radio telescopes, the VLA in the USA, here's the 18F in Australia, and the GMRT in India. They all use the system of aperture synthesis that Martin Ryle pioneered and for which he got the Nobel Prize. His ultimate achievement was the 5-kilometre telescope, and so over a period of 25 years, the sensitivity of the telescopes had increased by a factor of 1 million, and the imaging capability had gone from huge beams this size down to the resolution approaching optical telescopes. It's a fantastic development, and that is, and showed just how important radio astronomy was for all of these subjects. And just here's one of the examples of the new map of the radio galaxy Cygnus A made with the VLA, and you can see the huge wealth of structure. What's going on is illustrated by this little PowerPoint animation. This is what you call a Bill Gates animation showing what's going on. The blobs are just going out from the center, being powered by jets from the center. There it goes. Is that? If you can do that using PowerPoint, you know how to use PowerPoint, right? But that's what's going on. We've got these relativistic jets of materials blowing these bubbles out into intergalactic space. This is all to the correct scale, so you can see that these clouds of particles are, again, diffusing into intergalactic space. This is all relativistic particles, so we need to confine it somehow, and this X-ray image obtained by the Cambridge Observatory shows that if you do the same thing here is all the hot gas at temperature of around about 10 to 100 million degrees, which is providing the confining pressure to hold in the relativist particles. This is just my daytime job to talk about these things, you understand? This is Meanwhile, Tony Hewish, again out of the observatory, was studying the twinkling of the radio sources, because some of the compact quasars that would be discovered were seen to twinkle, and he was trying to understand what was going on. So he got a grant to build this large array to study the twinkling of the radio sources. Here's Tony with the array, and as I always tell people, the radio telescope is the thing which looks like a vineyard in the front, not the telescope at the back. It's a low-frequency array, so it can be done with this quite simple technology. Well, here's Jocelyn, who was the co-discoverer of these remarkable things called pulsars. What Jocelyn's job was to commission the telescope, and here's one of the first records obtained with the telescope. And the reason that Jocelyn was such a fabulous research student is that you see there's a little signal there, and that was a farmer with an unsuppressed tractor. It's just tractor noise, right? And here is something which you recognise was not a tractor, right? And in fact, it has got a quite different signature. You see it's asymmetric as compared with the symmetry of the interference there. This thing disappeared for about 2 months, and then in November it reappeared, and this is showing the pulses with these are the 1 second markers here, and you can see the pulses are pointing downwards. That's just the way that the picture is drawn. But this was a totally unprecedented astronomical phenomena. This is an astronomical object pulsing once per second. Now, it wasn't long before people realized that these were the enigmatic neutron stars discovered by a tech that nobody had thought of. Nobody thought of looking at it this way. Franco Pacini had suggested it might be possible, but nobody took it seriously. It came as a complete surprise that these are magnetized rotating neutron stars. They are very massive, they are very compact. They've got the whole mass of the Sun, about the mass of the Sun, with a radius of 10 kilometers, and they're rotating about once per second. Don't go near it. These are one hell of objects, right? In fact, the gravitational fields are so strong, if you stood on the surface of that thing, you get ripped apart by the differential gravitational. Don't go near them. That's a message. And the root causes for the pulses is simply that the radiation's coming up beams out the poles, and every time the beam comes across your line of sight, you see one of these pulses. But this means the whole star is rotating about once per second to do that. Now, that was a crucial discovery because it led us to understand that there have to be these very compact objects. And these are objects which have almost collapsed to black holes I talked about earlier. In fact, if you just squeeze them a little bit, they would collapse to black holes. Now, again, another thing that was happening about the same time in 1964 was that Roger Taylor came back to Cambridge, and one of the problems that was becoming a little bit perplexing was why the abundance of helium was about 23% wherever you could look at it in the universe. It's a difficult element to observe, but wherever you saw it, it was about 23%. And that was much greater than you could get by stellar nucleosynthesis. Now, what Fred and Roger Taylor showed that you actually get that very naturally out of the Big Bang nucleosynthesis. As the universe cools down from a very high temperature, the nuclear reactions took place between the neutrons, protons, and they produce a lot of helium. It's a non-equilibrium process, and so you get lots and lots of helium occurring, as well as traces of deuterium, helium-3, and lithium-7. And just to show you how beautifully this works, you can work out how much helium, deuterium, helium-3, and lithium-7 you get as a function of density of matter in the universe. And I can put on this diagram what the observations show. There's the observed amount of helium-4, observed amount of deuterium, helium-3, lithium-7. And you can see for these sorts of values, you can explain the origin of all of these light elements, which are very, very difficult to explain otherwise astrophysically. And so this was evidence for the Big Bang, coming from, of all people, Fred Hoyle. Now, we thought he'd been converted. We should have known better. But it's another brilliant piece of astrophysics done by Fred and by Roger Taylor. The next year, the cosmic microwave background was discovered, and that was the convincing evidence for the hot Big Bang. This was a very intense background radiation discovered by Penzias and Wilson in 1965. It's got the perfect black body spectrum like that, which tells us that it must have been created by equilibrium processes in the very early universe. So this was the final coup de grace for the steady-state theory. Here's again one of the modern pictures showing the distribution of the microwave background on the sky. It's one of the most important tools we have now for studying the very, very early universe. But that's a different lecture. Well, just to conclude, this is the story. The Institute for Theoretical Astronomy was founded in 1967 by Fred. He got a 5-year grant from the Wolfson Foundation to set this up, and it was an extraordinarily successful 5 years as a pure research institute. 1972, it had to be taken over by the university, and then it was amalgamated after a fairly difficult time with the observatories to become the present Institute of Astronomy, which is done quite fabulously well. Well, the next stage then in this history is just about to come about, and that is the Kavli Institute of Cosmology. This has been made possible by an endowment from the Kavli Foundation. What it's going to do is to bring together all expertise in cosmology from the Institute of Astronomy, from the Cavendish Laboratory, and from the Department of Applied Mathematics and Theoretical Physics into one specially designed building in the grounds of the IOA. So after all of the agonies of the past, we're looking forward to a future where all the astronomers in Cambridge will join together and take forward this fantastic legacy of Cambridge astronomy. Thank you very much.